Okay, hi again. This is experiment number 10 now. Entropy, Gibbs free energy, and the reaction quotient. The good news about this lab is that I understand it doesn't take that long to perform. The bad news is that if you look down here, there are 11, count them, 11 calculations which we'll be doing. So if you can understand the calculations, you'll be far better off for this experiment. The purpose is twofold. One, to find the change in entropy, that's delta S, for dissolving some sodium nitrate. The other purpose is to find the Q value, which is the reaction quotient for dissolving some calcium chloride. Well, that sounds easy enough. Let's make some predictions. Well, if we're going to dissolve sodium nitrate, it's going to break it apart, isn't it? It's almost like a decomposition reaction when you think about it. One thing turns into two things. I think you should be able to predict something about the entropy change. In other words, the increase or decrease in randomness based on that simple process. The Q value, that's the measure of the K value in reality, and so a high value would be a large K, would be a very forward-moving reaction. But two things. One, it's hard to predict what that value might actually be, and two, in practice for this experiment, you'll be graded based on the correctness of your calculation, not its accuracy. In other words, if you do the calculation correctly, but your numbers are a bit off, you don't lose any credit. On the other hand, for the entropy change, you will be graded. That's where your accuracy grade comes from. Okay, there was a pre-lab where they asked you to calculate the standard entropy change and the standard free energy change, that's right here, for the calcium chloride dissolution process, which is shown there. I did get some emails from people who said, I have no idea how to do that. A hint would be to use the thermodynamic data that's in the Chang textbook on page A3. You could try using some standard values from online. In fact, I did that, and my values were off by as much as 20%. So I recommend you either look up or obtain the thermodynamic data on page A3. And recall that we can get these standard numbers, delta H, delta S, delta G. I showed it for delta H actually, but this can be replaced with a S or a G of the products minus the reactants. Don't forget to use the coefficients, and one does show up right here. Okay, let's get right to the calculations. I've set this up as simply as I can, showing the sodium nitrate calculation where we want delta S, there it is, and the calcium chloride calculation where we want Q, and there that is. So I'm going to start with what you need, and then we'll work our way backwards, saying, well, how are we going to get that? I hope you understand that. Which means probably in practice you'll be working your way from right to left as you get to the desired number. Okay, how are we going to get the change in entropy by dissolving some sodium nitrate? Well, we take a measured amount of it, we throw it in water in a well-insulated container, otherwise known as a calorimeter, and we have two things, the initial temperature, and I guess the other thing would be the change in temperature. From that, we can calculate the heat that it either evolved or required. Recall that Q is equal to mc delta T, and the enthalpy is simply Q per mole. So if we have the mass of the solution, which means both the solvent and the solute, we can multiply that by the specific heat of water. I mean, it should be the specific heat of solution, but there's not much sodium nitrate in there. And that's joules per gram degrees Celsius. That should be a superscript there. And then measure the change in temperature. Now technically that should be Kelvin, but the change in temperature is the same whether it's Celsius or Kelvin, since you just add 273. So that's your delta T. And that would be your joules per gram degree Celsius. You can then change it to delta H by dividing by the molecular weight of the sample. And that'll give you the delta H in joules per mole. T, we also need to get the change in entropy is simply the initial temperature of the calorimeter, and for that be sure to use Kelvin. Let's use a negative value for Q since it should be releasing some heat. Always use your Kelvin, and you should calculate the change in the entropy. Since this is a spontaneous process, this will give us the minimum entropy value. Okay, that's the first calculation. Hope you understood that. The second one's slightly more involved. In this case, we want to get Q from dissolving the calcium chloride. Where do we get it from? Well, here's the calculation right here. The standard change in the free energy is equal to the change in the free energy that's measured, minus a number, R, times the temperature, which once again will be the initial calorimeter temperature, times the natural log of Q. And we're solving for Q, so we need everything else. Well, we got some freebies right off the bat. R is just a number. T is just that initial temperature of the calorimeter. And in fact, delta G under standard conditions isn't too bad because we calculated it right there in the Prelab. The only one that we have to work out is the measured change in free energy. And as you might guess, that uses the free energy formula. Delta G equals delta H minus T delta S. So we're going to need all these to get delta G. Do we have all those? Delta S. We're going to use the ones under standard conditions. We calculate that in our Prelab. Careful of your units. You should be looking at joules per mole Kelvin divided, not kilojoules. Here's your calorimeter temperature. That's an easy one too. And delta H, well, we've done that before, right here for sodium nitrate. Do the same thing with your change in temperature shown right here to get your delta H for the calcium chloride. Once you do that, you have everything you need to get delta G. Delta G plugs in there, and you'll have everything except Q. Solve for Q. If you're worried about the natural log, do your best you can to solve it, and then make sure all these numbers punch in and to ensure that you've done it correctly. Okay, those are the two calculations. If that makes sense to you, you should be in good shape. Okay, let's go over the summarized procedure. There's not too much really. Well, let's start with the sodium nitrate. We need to grind some of it up and then put it in the calorimeter. Follow the instructions. It does use Logger Pro. Just when you thought you were done using that program, here it comes up again. And we'll be doing that 3 times to get our delta T. When you get the change in temperature, you can then run your calculations. Okay, so that's right there. That's half the experiment there. Now we're going to do the same for calcium chloride, but I received some big warnings not to grind it up because it's ridiculously hygroscopic and can turn into goo. So just use it as is. Get your 3 trials. For this one, you may end up with a supercooling region, and if you do, just simply omit it. If the temperature goes down and then bounces back up, you should omit that supercooled region and just record used for your final temperature, the nice flat baseline there. So if that crops up, that's what you want to do. Okay, a few notes. The solids are spherical in nature, so they're like tiny little ball bearings, so don't try weighing them on the weighing paper. They will roll off and cause a big mess. So you do use the weighing boats. Their actual experiments may not take that long. But be sure you do your math before leaving. I can assist you when you need it for the calculations. I won't do them for you, but I might be able to, let you know how it's going. Use the distilled water. When you're doing your data collection for temperature initial and temperature final, be sure to start it before collecting your data, and I think that's probably in the procedure. Do be aware that this do not grind right here is an alteration to the procedure. If you follow the procedure, it'll ask you to grind it up in the mortar and pestles. Don't do that. You might want to make a note right now in your procedure. Do not grind the calcium chloride. Okay, where were we? We do need 2 graphs. One of these for potassium nitrate. Now it's sodium nitrate. That should say sodium. And one of these for the calcium chloride. Do note that in terms of getting a nice high grade in this lab, the accuracy counts for the change in entropy of the sodium nitrate, but we'll be checking only that you did your calculation correctly for Q. So even if your numbers are a little bit off in here, and I doubt they will be, they probably should be as good as for this one, then you'll get full credit. Omit the supercooling region, I already mentioned that. And here's the 11 calculations that I'd like to see in your lab report. This is by far the most calculations we've ever done for a lab report. If you want to get a good grade, number them 1 through 11 so I can follow them very clearly. The first 2 are the Prelab calculations, which should use this formula here to get the standard entropy change for sodium nitrate. I will be checking your units. And to get the change in free energy under standard conditions for sodium nitrate. Is that right? Oh, it's not right. Take a look at this. It's for calcium chloride. So this is a typo right here. This should say calcium chloride. That should say calcium chloride. I hope that's clear. If you're listening to this, hopefully you've already done the pre-lab and you know that. Now for sodium nitrate, let's calculate the Q value, which is MC delta T. That'll spit out joules per gram. Let's switch that into the change in enthalpy, which just turned grams into moles. And sodium nitrate, I believe it's about 85 grams per mole, but go ahead and check it. Then calculate your change in entropy in joules per mole using this formula here. You'll have each of 3 trials calculated and then take the average, and that is your calculation number 6. For the calcium chloride, let's calculate Q in joules per gram, which is right there. Now to get there, I think you need some of this stuff intermediate. It's a kind of a, should have been a little bit more at the end perhaps. Let's get delta H the same way we got it for sodium nitrate by first getting Q, converting it into delta H, go from joules per gram to joules per mole. That should be easy. Calculate the change in free energy. That's the summary right here. Just follow these well laid out instructions there and you should get your change in free energy. Then finally plug it all into here and get your Q value, and you'll be doing it 3 times, so I'd like to see 3 Q values. And then finally calculation number 11 is the average. If you get all these numbers roughed out before you leave the lab, you'll feel better knowing that you can grade it all. You can get it all nice and get a nice high grade. Okay, this is experiment number 10. Entropy, Gibbs free energy, and the reaction quotient.